In the last video, we developed the Tonti diagram. There are lots of useful information we can deduce from the Tonti diagram, but before we can do that, we need some concepts from linear algebra, and that's what we'll do in this video. We'll develop 7 ideas related to linear algebra. First, we talk about dot product. You'll recall from 3D, from statics and so on, that if x is x1i plus x2j plus x3k, and y is y1i plus y2i plus y3k, then the dot product of x and y, and we'll use the notation with the brackets for the dot product like this, is x1y1 plus x2y2 plus x3y3, or we can write that with summation notation, sum I equals 1 to 3 of xi, yi. We can also write this as x transpose y. In general, if x and y are n-dimensional vectors, so that they have n components each, then we can define the dot product by analogy. The dot product of x and y is the sum I equals 1 to n, xi, yi, which we can again write as x transpose y. We're interested in the dot product because we will do dot products of external load and displacement P transpose U, or member force and change in length F transpose delta. The second idea is orthogonality. Again, recall in 3D that if two vectors are orthogonal, then their dot product is 0. In other words, the two vectors are perpendicular to each other. This idea extends to general n-dimensional vectors. So if we have two vectors x and y, then they're orthogonal if the dot product is 0 or x transpose y is 0. The third idea is matrix transpose. So if we have an m by n matrix, its transpose is the n by m matrix, which is obtained by switching the rows and columns. And here's a little simple example. So if we transpose the matrix, then the rows and columns are switched. The fourth idea is the transpose of a product of a matrix. So if we have a product AB of two matrices and we transposed it, the answer is B transpose A transpose. So the transpose of product of two matrices is the product of transposes, but in the reverse order. The next idea is what is a symmetric matrix. So a square matrix is called symmetric if the transpose of the matrix is itself. So here's an example. Symmetric matrix, and we see how the elements of the matrix are mirrored about the diagonal. The next idea is a positive definite matrix. This may be something new. So a symmetric matrix is called positive definite if for any non-zero vector, if we do the operation x transpose ax, we get something greater than 0. So this is generalization of a positive number, a positive definite matrix. So just an exercise and application of the definition. Can we say if the matrix 1, 2, 2 minus 1 is positive definite? Can we say if the matrix 1, 2, 2, 1 is positive definite? What I'd like you to do is to pause the video at this point and think about these questions. So the idea of positive definiteness is useful because the stiffness matrix of a stable structure is always positive definite. And we'll talk more about this in assignments 3 and 4. The last idea for this video is that of Cholesky decomposition. This is an efficient way of doing Gauss elimination. You're probably familiar with Gauss elimination from ES 230 and courses like that. So it's an efficient way of doing Gauss elimination for symmetric positive definite matrices. We know what that means now. So if a matrix is symmetric positive definite, it can be decomposed in the form A equals R transpose R, where R is a lower triangular matrix. In MATLAB, the Cholesky decomposition can be computed in this way using the function chol. So I encourage you to look at the help for chol in MATLAB. We'll tell you more. So this is useful for us because it's a it'll give an error if you try to do Chol on a matrix that is not symmetric positive. So it'll be useful for us to troubleshoot stiffness matrices.